Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our fourth set of notes, which is the first part of Section 3 in Chapter 17, dealing with strong titrations. Now, we talked about titrations before. Remember, it's a technique where you take a known concentration of a substance in a burette and titrate it against by adding it to its opposite. So in this case, we have a strong base in the burette, and we're titrating it against a strong acid, which is in the beaker. So in a strong titration, both our acid and our base are strong. Now we can use a pH meter or an indicator to tell when we've reached the end of our titration. And if you do it right, the end of the titration should be when you reach what's called the equivalence point. It's the point at which the stoichiometric amounts of acid and base are equal. And what I really mean by that is our moles of H plus equals our moles of OH minus, and they perfectly have neutralized each other to make water. Now, when a strong titration occurs, there's a big swing in pH. So that's how you use a pH meter. When you see the pH rapidly going up with the addition of one drop, you know your equivalence point. The other thing you can use is a color change of an indicator that during that big swing in pH, the color of that indicator changes. So when one drop changes you from one color to the other, you know that you're going to stop. And you need to match your endpoint to the equivalence point, the point at which the moles of H plus and OH minus are equal to each other. Now, there's really four regions to a titration that you need to understand. And really, you need to be able to calculate the pH, and you need to be able to describe what is there. So what species are present in each region. The first region is before the titration starts. The second region is before the equivalence point, what's happening with pH and what's in the flask. Then at the equivalence point, and then finally you need to be able to calculate pH past the equivalence point. So those are our four fundamental regions in a titration that we need to be able to understand what's there and what's the pH. Now at the start of the pH, or the start of the titration, we haven't added any base yet, so we call this the initial acid period. Literally, as a strong acid, we can calculate the pH from the concentration of the acid for everything but sulfuric acid, because we haven't neutralized the acid yet. And strong acids, we can directly calculate their pH using the negative log of the acid concentration. That's going to give us the pH. So that's how we find our pH at the beginning. We just take the negative log of the acid concentration. Now, what species is present? Well, as a strong acid, it's dissociated 100%. So we basically have H plus, and then we have our anion, in this case Cl minus, since it was HCl. We've got 100% broken apart, so there is no HCl stuck together in its molecular form. They've disassociated 100%. Now, the second part of the titration gets a little bit more complicated because we've started to neutralize the acid with the base. Now, remember the stoichiometry for our neutralization is 1-to-1. When taking H plus and reacting with OH minus to make water, it's a 1-to-1 stoichiometry. So if we can establish the moles of H plus that we have at this point, and remember, that's going to be our initial number of moles of H plus. That's what we start with. If we subtract that from that, the number of moles of OH we added, we can find out how many moles of H plus are left, because we're going to have more H plus than OH minus at this point. Now that gives us the moles of H plus, but molarity is moles per liter, so we take the moles of H plus and divide it by the total volume in liters. And that would give us the concentration of the H plus or H3O plus. Take the negative log of that and you've got the pH. Now, what exists in the flask at this point? Well, we still have our H plus and Cl minus floating around, but we've used some of the H pluses up, and we've converted them into OH minuses. So, or I should say, we've neutralized some of our H pluses with OH minus. So you'll notice our amount of Cl minus is the same. We're not reacting that. Our amount of H plus has gone down, and we now also have sodium ions from the strong base. We don't have any OH minus from the strong base since we used it up, but we do have Na plus floating around. So that's what we have in the flask in region 2. Now the next region is when we're at the equivalence point. Now at the equivalence point, remember the moles of H plus equal the moles of OH minus. So if it's a monoprotic acid and a monobasic base, it's fairly simple. The moles of acid equal the moles of the base. And what's going to happen is the solution is going to contain only water and the salt from the cation of the strong base and the anion from the strong acid. So in this case, it was HCl. So the spectator ion Cl minus is still there floating around from the HCl. And the Na plus that we added from the strong base is there, but all of the H plus and OH minus at this point are gone. And what we have is water with Na plus and Cl minus floating around in it. And notice we have equal amounts of each. And the H plus and the OH minus have canceled each other perfectly. So what we're left with is a true neutral solution. Our pH is going to be 7 in a strong titration. And then you need to understand just before we reach that, you're going to get a huge swing in pH. So we're going to look at a just before and just after pH in our sample problem for calculating pHs. So just before that, we get to the equivalence point. That's when your pH changes very dramatically. Look at this huge swing, all the way from down around 3 to up above 10. So because it goes through such a big swing, we can actually pick several different indicators that change color in that range and work. We can use phenolphthalein as it shows here, or methyl red. Both of those would change color in that big swing, so both of those would work to say when we're at the equivalence point. Now, once we get to the equivalence point, remember we go through that rapid change, and then after that, notice the pH is slowly rising again. And that's because now we're in our excess base region. We've used up all of our strong acid, and now we're slowly just adding more excess base, and that's going to slowly increase the pH. Now, how do we calculate that pH? Well, in this case, we're going to have H plus used up and OH minus left over. So if we take the moles of OH minus from our strong base and subtract the moles of H plus from our strong acid, we would find out how many moles of OH minus are left. Divide that by the total volume in liters. Remember, that's a total volume. That's very important. And that's going to give us the concentration of the OH minus. So if we want pH, we have to take the negative log of that and subtract it from 14 to get our pH. Now, what species exist in this region in a strong? Well, remember, we have OH minus now floating around, so we should see that in the beaker because it's not used up anymore. All of our H plus is gone. We're still adding more base, so the amount of sodium ions is increasing, but we've got the same amount of our chloride ions that we had through the whole titration still floating around. So those are the species that are present after we reach the equivalence point. So you should be able to understand how to calculate the pH and what exists in the beaker at each of those regions. The other thing you should be able to do is choose an appropriate indicator. And I briefly mentioned this before. Remember, our indicator should change color around the equivalence point. So in a strong acid base, it's such a big swing, 4 to 10, that there's actually a number of different indicators that would work fine. Now, before we do a pH problem, I want to remind you of something that we did way back in Chapter 4, and that is calculate the what volume from our burette of our base we need to add to reach the equivalence point. If we're calculating the pH at various spots, and things are a little bit different when we're before the equivalence point, at the equivalence point, and after the equivalence point, it's really nice to know up front what volume would I need of my base to reach my equivalence point? Because that's really what we're going to look at is we've got a set amount of acid and its concentration. We know the concentration of the base, and we're going to be told how much of that base we've added. So if you recall, it's a stoichiometry calculation to find out the neutralization equivalence point. So in this particular case, we're looking at an example where we've got 45 milliliters of 0.15 molar HCl, and that's being titrated with 0.42 molar CaOH2. So the base is in the burette because it's being titrated with that amount, and the acid is what is in the flask. And that's why we know its volume and concentration. So how do we go from this information to what's the equivalence point volume? Well, you just do a 3-step stoichiometry. First, we need for any stoichiometry the reaction that's going to happen, and this is critical because it's not a one-to-one stoichiometry here. When you look at the reaction of HCl and CaOH2 to make water and calcium chloride, it's a 2-to-1 stoichiometry. So you have to start by writing the neutralization reaction, and then from there you do the stoichiometry. We know we started with 45 milliliters. Remember, our job in any stoichiometry calculation is to get to our moles of our first substance, so we can change from moles of one substance to moles of the other, and then get out of moles to whatever unit we're trying to look for. So in this case, since we're dealing with volumes, we're going to be using molarities. Now, the shortcut I did here, which is something I taught you back in first semester, is that's the molarity in moles per liter. But remember, It's also the number of moles in 1,000 milliliters. And now I don't have to do an extra step or convert the 45 milliliters in my head to liters. It's not that that's hard, but this is a little quicker and easier, and you don't have to think as much when you're doing it. So notice I did the same thing at the end. It was 0.42 molar CaOH2, so that's the number of moles in 1,000 milliliters. So what this tells me is I have to add 8 milliliters of my calcium hydroxide to reach my equivalence point. The point at which they've perfectly neutralized each other and my pH is 7. Anything less than 8 milliliters and I'm before the equivalence point. Anything after and I'm after the equivalence point. So up front, it's nice to know this. So when we start this problem to calculate the pH for this titration, in the burette we have 0.100 molar NaOH, and that's being added or titrated with HCl here. Or I should say the HCl is being titrated with the NaOH. So we've got the HCl in the flask, 50 milliliters of 0.100 molar, and that's what's in the burette, 0.100 molar. Now the question is asking us, what is the pH of the solution when we're at 49.0 milliliters and we're at 51.0 milliliters? Now remember, it's really convenient up front to know what the equivalence point volume of our base is going to be. So the first thing we need to do is write the neutralization reaction. It's HCl and NaOH, so it's a nice simple 1-to-1 stoichiometry. And then you convert your volume of your acid to moles, then moles of acid to moles of base, and then use the molarity of the base to convert that mole amount of base to the volume. So up front here, I can do this calculation right away, and I can see that after I do the stoichiometry, I know I'm at the equivalence point at 50.0 milliliters. So notice what we're looking at is right before the equivalence point and right after the equivalence point. We should be seeing a very big change in pH between these two because we're right close to the equivalence point. So let's go through and calculate both. Now to establish which of the 4 regions, which honestly we already know, we're starting before the equivalence point. But if you're not sure, what you really need to do is find the moles of your H plus from your strong acid and the moles of OH minus from your strong base and compare the two. So in this particular case, it was 0.0500 liters. It was 50 milliliters. And we know the concentration of the acid is 0.100 moles per 1 liter. It was 0.100 molar. So we have at the very beginning here 0.00500 moles of H plus. That's before we add any base. So that's our starting point for the H plus. Now we need to do the same thing for our OH minus at the region we're at. So we added 49.0 milliliters. So the volume in liters times the molarity of the NaOH would tell us how many moles of OH minus we've got. So notice at the beginning we had 0.00500 moles of H plus, and we just added 0.00490 moles of OH minus. We're clearly before the equivalence point because the OH minus is less than the H plus, but we're close because they're close to equal. Now remember, this is a 1-to-1 neutralization, so the exact amount of OH minus we have is exactly how much H plus we're going to consume. So we subtract those two and we can see we've used up all the OH minus and we now have that much H plus left. So now that I've got the concentration of the H plus, if I want to find the pH, I need to do the right math. Remember, that's how many moles I've got. We have to do the stoichiometry from a mole standpoint and then divide by the total volume in liters to get it to a concentration. Now in this case, we added 50 milliliters and 49 milliliters, so we have a total of 99 milliliters, which is 0.099 liters. So if we take our mole amount, which we just calculated of H plus, and divide by that total volume in liters, then we calculate the H plus concentration. Take the negative log of that, and we've got the pH. So you can see here to 2 sig figs, we are starting out at 3.00 as our pH value. So that is our initial pH in this case. Now, yes, technically, if you want to go to correct sig figs, this would be 3.00. Well, actually, no, it should be down to 2 sig figs because after the subtraction, we were down to 2 here. So that is the correct value. Remember, the number of decimal places in a p-value is the number of sig figs that we should have. Now, after our pH, or I should say after our equivalence point, which is what 51 milliliters is, notice we don't have to recalculate our H plus. That's going to stay the same because how much H plus we start with never changed. What's going to change is how much of it is left at different spots in the titration. So that number is the same. We don't need to redo it, but we need to take 51 milliliters and calculate how many moles of OH minus that would be. Now notice OH minus is bigger than H plus. That's our dead giveaway. We're in the final region. We're past the equivalence point. So we have to subtract the H plus now from the OH minus to find out how much OH minus is left and divide it by the total volume. We had 50 and we had 51. That's 101 milliliters, which is 0.101 liters. And remember, this is OH minus. So if we want the pH and we take the negative log of that, we get the pOH. We have to subtract it from 14 to get the pH. And notice after the subtraction, it jumps all the way up to 11. We went through a huge swing. In 2 milliliters, we went from 3 pH to 11 pH. And that's what happens around the equivalence point. There's a huge swing in pH, and we can clearly see that. And that ends our notes over strong titrations.